Hi. Yeah, so here's your kind of run-of-the-mill proportion, and that is an equation where both sides of the equal sign have ratios. So these are ratios, they're comparisons between two numbers, 1 to 2, 3 to 6, and they are equal to each other. Their value is equal. So if you were to evaluate each one, they would have equal values. So I'm going to show you how to describe proportions in a different way. Actually, you're going to be able to write an equation that describes the same proportion, but it'll allow you to expand to, instead of just having two ratios like this, you could have an infinite number of ratios. I mean, it's really going to open things up for you, I think. Okay, so uh, let's talk about the constant of proportionality because we're going to need that to write our equation. So the constant of proportionality is the value of the proportional ratios. So, for example, let's evaluate each one of these. These two ratios are proportional. We know that because there's an equal sign here. And let's evaluate them. So 1 divided by 2 is zero point 0.5. And 3 divided by 6, I'll just prove it. It's 0.5. It's 3 divided by 6, zero point 0.5. Also, so these are equivalent fractions, equivalent ratios. So the constant of proportionality is zero point 0.5. So what that means is that if we were to take the bottom number and multiply it by the constant of proportionality, that'll give us the top number. So for example, if I multiply 6 by zero point 0.5, also known as 1/2, I'll get 3. So we could actually use this constant of proportion to write an equation that describes this proportion. So it would go like this. The height of the Mathceratops is equal to the width times zero point 0.5. So take whatever the width is, take that and multiply it by zero point 0.5 and you'll get the height. So let's test that. If we have a Mathceratops with width of 6, zero point 0.5 times 6 is what? 6 times zero point 0.5 equal to 3. So that works for this, right? So if we have this equation though, that means not only can we deal with these two particular Mathceratopses, the one that's 1 meter high by 2 meters wide, or the one that's 3 meters high by 6 meters wide, but we can do any size. So like a gigantic Mathceratops, like boom, like this guy, right? Let's just so let's say the width is, I don't know, let's say it's 100 meters. So h is equal to, oh, where'd my color go? Let's make this blue. H is equal to zero point 0.5 times the width. So if I have a width of 100 meters, I can plug that in to this equation, into the W. Okay, I meant to point to the W. And I'll get the height. So 100 meters times zero point 0.5 is 50 meters. So the height would be 50 meters. So I could write that fraction like this. If we're going back to how we started things, it'd be 50 meters tall and 100 meters wide. And this equation allowed me to figure that out based on one of the measurements.